Okay. Now, you see we have got 2n number of poles, okay, but 2n number of poles of what? Of this function, okay, roots of this function or poles of this overall function. Okay. What are the poles? These poles are nothing but the poles of this product H A S into H A minus S. H A S is of this form, in general form, H A minus S is just S replaced by minus S, that kind of form. That is H A S you can write as N S by d S, where N S is this, d S is this, and then H A minus S is N minus S divided by d minus S. Now, we have seen that if there is a pole, if H A S has a pole at alpha, so there will be in the denominator a factor like this S minus alpha. Then H A minus S also will have a pole at minus alpha. So, there will be a term like minus S minus alpha, minus can be taken out, right. So, that means for this product in the denominator, if there is one pole at alpha, there is another pole at minus alpha, which means 2n poles will be such that if there is one pole on say left hand side, if you call it say suppose some S, if you call it some S0, okay, then there will be another pole at minus S0. If S0 is say A0 plus JB0, A0 here is say negative, B0 is for this much is B0, JB0 and A0 is negative, minus S0 means minus A0 minus JB0. So, minus A0 it will be on this side, okay, and this side. All right. So, if there is a pole at S0, there is a pole at minus. That is why out of the 2n poles, half there is n number of poles will be on this side, and for every pole at for every pole say at S equal to S0 or whatever, there will be a corresponding pole on the right hand side at minus of that S0, or if you call it S1 minus of S1 like that. Okay. So, now I know how the poles will be. The poles are all the poles are separated by this angle pi by n, because if from k equal to 1 you go to again k equal to 2, increment will be pi by n. So, 2 pi and 2n angles, 2n poles. So, 2 pi divided by 2n, so pi by n. So, all the poles they are separated uniformly by pi by n angle. And there is one more property that we have just discussed, that is if there is a pole at any value of s, say S0, then there will be another pole at minus S0, which means if S0 is on the left hand side, that is real part negative, suppose imaginary part positive, minus S0 will be on the right hand side, real part positive and imaginary part may be negative, okay, and vice versa. Then what we do is this, we take all the left half plane poles, okay, maybe alpha 0, alpha 1, say suppose this is alpha 0, suppose this is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay. So, if it is alpha 1, this is minus alpha 1, if it is alpha 2, it is minus alpha 2, like that. So, we do not consider them, we consider the alpha 0, alpha 1 dot 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 say alpha 5. We consider these factors S minus alpha 0, S minus alpha 1, okay, dot 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 up to S minus alpha 5. Okay. These poles, these I give to HAS, that is HAS is this by 1. Okay. That is I assign these poles on the left hand side of the S plane to HAS, and then obviously HA minus S will be what? It will be a 1 by minus S minus alpha 0, minus S minus alpha 1, minus S minus alpha 5, so on and so forth. And so HAS into HA minus S, I will have all the poles on alpha 0 minus alpha 0, alpha 1 minus alpha 1. So, out of 2n poles, it is my privilege, my choice, which capital N number of poles to assign to HAS and which to minus S. I will assign so that all these left half plane poles come under HAS, and obviously their negative versions which are on the right hand side, they go to HA minus S, and HAS into HA minus S in that case will be equating to this function. Okay, because I found out the roots by equating this to 0 and then 2n roots, so s minus this, s minus g, s minus alpha 0, s minus alpha 1 dot 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 dot, okay, up to s minus alpha 2n, that was the product, out of which n factors I give to HAS, taking care so that the corresponding roots are on this side, left hand side, and thereby automatically the roots on the right hand side go to HA minuses, but product remains this, which is what I wanted from the frequency response. But what do I gain by choosing HAS like this? Here all the poles are on the left half plane, okay, that is on the left hand side of the j omega axis, which means the system will be causal and stable, okay, that is what is assured. So, by this process you generate the Butterworth function. If it is, I mean n, if it is nth, if you have got capital N number of, rather 2n number of poles, so capital N goes to this side to HAS, and the HAS that you get will be 1 by s minus alpha 0, s minus alpha 1 dot up to s minus alpha capital N, this product, and that will be nth order Butterworth function. Nth order, the denominator will be nth order Butterworth polynomial, and the filter transfer function will be nth order Butterworth filter. Okay. This is just one approximation. There are other approximations possible, Chebyshev, you know, I mean, and there are many others. Okay. Elliptic and all that. They all maintain stability, causality, rationality, and they try to approximate this frequency response again by some good curve. All right. Now, the question is, suppose my task is to design an IIR filter. So, fine, IIR low pass filter, I proceed in the analogous way, that suppose I can, since I cannot match both the magnitude and frequency phase, I concentrate on the magnitude part only, this square. So, this will be periodic again from minus pi to pi, because this basic function is periodic. So, it should be ideally this, some omega c, now the digital frequency pi minus pi, and then again you have got those periodic parts. Okay. This is what I want to design, this is an ideal low pass filter. Okay. But ideal low pass filter means, suppose I want to design a Butterworth filter. Okay. So, therefore, this will be approximated by a function like this. What is this function? This function will be as before 1 plus, if the height is 1 plus omega, in this case just omega by omega c whole to the power say 2n, if it is an 2nth order function. Okay. Sorry, this is small omega, I am very sorry. This is not HA anymore. This is a bad habit. I was carrying, going on with HA, so HA is coming here. It is purely digital. So, there is no HA, there is no capital omega in this diagram. So, this should be my Butterworth filter. Ideally, this should be a digital Butterworth filter. But point is, what is h to the power j omega? This is of the form So, here lies the big difference with analog filter. In analog filters, this was polynomial clearly in terms of capital omega in the denominator. Therefore, you could approximate this given function by 1 by a polynomial in capital omega, and then you could write this left hand side as HAS, HA minus S, as with S equal to j omega. Okay, and then from j omega you can write as j omega by j omega c and replace j omega by S and go on. Okay, the way we did, because we know HAS is of this form, H j omega is also of this form. It was a polynomial in S, it is a polynomial in omega, and I approximated it by this omega by omega c here. So, it is a polynomial in omega, but in this case I want a polynomial in small omega, like, because it is Butterworth, but my numerator is not a function of small, not in terms of powers of small omega, it is in terms of powers of e to the power j omega. That is, this is not equal to b on j small omega plus b q j small omega whole to the power q. This is what I would have loved to have, you know, j omega plus dot 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 but this is not the case, because we know from our discussion so far that discrete time Fourier transform, there is a transfer function of a rational system is of this form. Numerator is a polynomial, but not in terms of small omega, it is a polynomial in terms of e to the power minus j omega. This also is denominator also is a polynomial in terms of e to the power minus j omega, but my function by which I am approximate the ideal filter characteristics, it is in terms of omega, omega to the power 2n. So, I cannot directly use this form to obtain this. This is a big problem. Then the question is how to design this filter. So, one technique, there is a basic technique called impulse invariance method. Here, first assume that this small omega c is very quite far from pi, and the filter order, this approximation is valid, I am trying to make this approximation, but the order is very large, so that this becomes 0 or almost 0 very quickly, and when it goes to pi it is almost 0, it is gone. Okay. Theoretically there may be very small value, but gone. First assume this. Then what we will assume? Next we assume that there is one analog filter with transfer function this in terms of Laplace transform H A S, and this has got this time function. Okay. We will assume that there is one such H A j omega which is band limited, which is also Butterworth band limited, that is going down to 0 like this, and we sample it, sample this H A t above Nyquist rate, either at Nyquist rate or above Nyquist rate. So, we choose a sampling period t, where we choose a sampling period t. So, in that case, from this we construct, if it is 1, we construct one function, Butterworth function, but this would be capital T times this function, right. You remember when we sample one analog signal and get a discrete time signal, even if we sample that higher than Nyquist rate, what happens? Discrete time Fourier transform is a replica of the analog Fourier transform, but there are some changes. From capital omega frequency we go to small omega frequency by this relation omega into t small omega, and there is a scaling by 1 by capital T, that is from analog to digital. When we go, we have a replica, but there is a scaling by 1 by t. So, here I am trying to go in the opposite direction, I am trying to construct one H j omega, so that mod H j omega square, okay, looks like this Butterworth function, is a Butterworth function. So, here originally it was 1, okay, this basic DTFT suppose was 1, and when you squared it, it is 1. So, now it will be multiplied by t square, okay, because DTFT has been a scaled version of this by 1 by t. So, if we take mod and square, it is 1 by t square of that. So, from here if you want to go back there, it will be t square times, this value will be t square, and this will be capital omega axis. Pi always corresponds to half sampling frequency. So, this will be half sampling frequency pi by t, and this will be capital omega c. All frequency omega will be nothing but small omega by t, there is a relation small omega by t radian per second. So, that is how you map at any small omega whatever is the value, that will come to corresponding capital omega, where capital omega is omega by t, t is your choice. So, thereby one plot is mapped to another plot, and capital omega c will have, which is small omega c by t. So, we will have a Butterworth function. This Butterworth function, since small omega c is much less than pi, capital omega c will be much less than pi by t, because this is omega by t, this is pi by t, and therefore, it will go down sharp, and n is large. So, it will go down sharp. So, when it reaches the half sampling frequency is almost 0, and therefore, it means that if I really use this t to sample, since the analog, this is band limited, the analog function is now band limited, it is almost 0 at half sampling frequency, there will be no aliasing. So, if HAT, the corresponding capital H omega is sampled with the sampling period capital T to generate Hn, that Hn will have a DTFT which will look like the original DTFT, analog Fourier transform. There will be no aliasing component. Okay. Then you take the Z transform of this Hn, and that will give rise to your filter, whose frequency response will be similar to the analog frequency response, and therefore magnitude response square will be same as the original magnitude response square. Okay, this is a FLUP. I repeat again. We have seen the difficulty in designing the IIR filter in the same way as we did in the analog case, because when I try to approximate this ideal filter, I have this kind of function, Butterworth function, where the denominator is a polynomial in omega. Okay. You see, then only if I put in a polynomial omega, then only I can say if omega is greater than omega c, it will be greater than 1, and this whole thing is raised to the power 2n, much less, it will be much higher than 1. So, 1 you ignore, 1 by this quantity, this is much higher than 1, so it will almost 0, so it will fall down. The moment I cross omega c, this function will go down, so start falling down rapidly and become 0. On the other hand, if omega is less than omega c, this is less than 1, so raised to the power 2n, which means it will be much less than 1. So, you can ignore it as compared to 1, and 1 by 1 is 1, so it will be flat. So, all this business I could do, because there was a direct polynomial directly in terms of small omega, but and that I wanted to have as the magnitude response. But H omega is of this form, B0 plus B1 e to the power minus j omega plus B2 e to the power minus j2 omega plus dot dot BQ e to the power minus j q omega, and denominator also. That is, it is a ratio of two polynomials, but polynomials are in terms of powers of e to the power minus j omega, not in terms of omega. That is the problem. Okay. That is the problem. So, therefore, the question arises as to then why, how can you design an IIR digital filter? Then we say, okay, first you start with this function. I will then construct a prototype analog low pass filter this way, that I assume that there was one analog Fourier transform, analog transfer function H j omega, and its corresponding inverse transform, that is time function, is H a t. That H j omega also is Butterworth type. Okay. And I assume that the corresponding time function will be sampled by a period t. Now, here if it is Butterworth, okay, when I go for constructing that analog low pass filter, first I will do these things. This will be the frequency transformation, or this will be the frequency transformation. At any small omega, whatever value we had here, that will go to corresponding capital omega by this relation. So, omega c will become capital omega c like this, pi will become pi by t, and so far so forth. So, I construct this function, I construct one giving this frequency response, magnitude response, I construct one analog magnitude response in this way. I choose one sampling period t, then using this relation capital omega is small omega by t, I transform this figure to this and multiply this by t square, and t is anything, t can be 1 also. Okay. So, then if it is pi, it is pi by t. If it is small omega c, it is omega c by t, that is capital omega c, and this is Butterworth. So, functionally it will be same, because shape of this response will be same as shape of this response. There is only frequency scaling. Okay. But since small omega c was quite far from pi and the order was large, it was going down to 0 before going to pi. Here also capital omega c will be quite less than pi by t and order is large, so it will go down to 0 before going to pi by t. Pi by t is the half sampling frequency. This means the signal is band limited and it becomes 0 before it reaches the half sampling frequency, which means sampling at the sampling period t by this sampling of this corresponding time function by the sampling period t, if I generate a sequence h n, that h n will have a frequency response which will be replica of this kind, magnitude response is replica of this kind without any aliasing. Pi by 2 will then become pi, capital C will become small omega c, height will become 1 like that. So, then by that process, that is by first constructing this analog prototype filter, that is start with this digital filter, then think about any I mean just choose any capital T, which in fact you can take to be 1. Then for that capital T, using that capital T and using this frequency transformation, you transform this magnitude response to an equivalent analog description, where every small omega will give rise to a capital omega, and also multiply this by t square. If t is 1, this t square is 1. So, this function will be an prototype magnitude response of an analog low pass filter, okay, with cutoff frequency capital omega c. But here this is pi, this is pi by t, this is small omega c, capital omega c. Since omega c was quite less than pi and order was large, this function became 0 before going to pi. Same applies here, capital omega c is less than pi by t, because capital omega c is omega c by t and this is pi by t. If omega c, small omega c is less than pi, much less than pi, omega c by t also much less than pi by t, and the order is large, so it will fall down to 0, which means when I reach the half sampling frequency, the signal is already band limited, it has already become 0. I mean, a frequency response, magnitude response has already become 0, which means if I take this h j omega and take the h a t, how to get the h j omega? I know it is now analog Butterworth of nth order. So, I know h a s, how to construct h a s. From h a s I can get h j omega by inverse Laplace transform, or by inverse analog Fourier transform, I can get this time function small h a t, and then I sample it at the sampling period t to generate h n. This h n, its discrete time Fourier transform, because of no aliasing, will be replica of this magnitude response. If you take the magnitude part and square, it will be replica of this, where pi by 2 will become pi, capital omega c will become small omega c, height will become 1. That is, I am going the reverse way. That is, it will give rise to the desired function. So, then what is the root? I repeat again, from the analog given digital this approximation in the DTFT in the magnitude response, okay, you construct from the that is desired magnitude response of the digital filter, which is of the Butterworth type in this case as an example. You construct an analog prototype magnitude response, analog low pass filter with magnitude response, a replica of that with this frequency transformation, that is choosing a sampling period capital T, you derive capital omega small omega by t. So, by this frequency mapping, you just map it here, pi becomes pi by t, omega c becomes capital omega c. It was going down to 0 before reaching pi, here also it will go down to 0, height will be t square, okay. And if it is of this shape, the shape will be same. So, this will be Butterworth again. So, you are designing now an analog Butterworth filter, okay, of cutoff frequency capital omega c and order n. So, you can design this h a s from this either by inverse Laplace transform or from h a j omega, that replaces by j omega, and by inverse analog Fourier transform, get the analog time function, then sample it, you get h n. This h n, I know its DTFT, if you take that h e to the power j omega, its magnitude square will be replica of this, because of no aliasing, because this function has become 0 before pi by t, and pi by t is a half sampling frequency. This h n, if you take z transform h z, that will give rise to this filter, okay, desired filter, all right, and it will be causal and stable easily, because h a t is how h a t is obtained by inverse analog Fourier transform, inverse Laplace transform of h a s, but h a s is stable and causal. Therefore, h a t is 0 on this side. If it is time x, it is 0 on this side. Here it can be anything, and this if you are sampling, you get h n, where h n is 0 on this side and h n is having non-zero values on this side of the origin, right. So, h n also causal, and if h n is stable, that is if this is finite, then if you take samples, take their magnitude and add, that obviously will be finite, because you are not even taking the intermediate values, okay. That will be finite. So, it will be absolutely summable. So, it will be causal and stable. Okay, we can also show it will be rational. It will be rational because HAS will have this kind of form, right? S minus alpha 0, S minus alpha 1, dot 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 dot, say by suppose 1. It will give rise to some first order factors like S minus, if you go for partial fraction these plus A2 S minus alpha 1 dot 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 dot. If you take the analog inverse Laplace transform, you will sample it at capital T. So, it will be A1 e to the power minus alpha 0 t, and since it is causal and stable, this plus A2 e to the power minus alpha 1 t, again u t, and dot 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 dot. Now, if I sample it at the chosen sampling period t, so Hn will be Hant, means alpha 0 n t un, because unt means same as un. UNT, okay, original analog unit step function at NT will be 1, okay, if n is positive, if n is negative it will be 0. So, you get same as UN. So, this and dot dot dot. If you take Z transform of this, so because of UN it will be A1 c to the power minus alpha 0 t whole to the power n, right, and this will have magnitude less than 1. Why? Because alpha 0 is on the it will be plus. If it is S plus alpha, it is minus alpha t. So, this is minus alpha 0, it is the power plus alpha 0 t plus alpha 1 t, like that. Okay. Now, it will give rise to, now one thing you see, alpha 0 is what? Is one pole, but it is lying on the left hand side of the S plane. So, its real part may be sigma 0, it is negative plus j omega 0. Okay, this is negative because it is lying on the left hand side of the j omega axis. So, e to the power alpha 0 t means e to the power minus sigma 0 t into e to the power minus j omega 0 t, right. All right, this is the quantity. If you call this quantity A, then what is mod A? Mod A will be mod of this into mod of this, but mod of this is 1, e to the power minus j anything, mod of this is 1. So, it will be, and this is positive, mod of this is this itself because this is always positive, this. But sigma 0, sorry, this is plus, because alpha 0 is sigma 0 plus j alpha 0, so plus. Okay, so it is about sigma 0 t, but sigma 0 is negative. So, to the power some negative into t, that is less than 1, which means this quantity, if you call it A to the power n, A is less than 1 in magnitude, mod A is less than 1. So, that means if you take the Z transform will exist, it will be this, and A is to the power alpha 0 t. So, alpha 0 t into Z inverse plus again similar things, and for this ROC will be, for this part ROC will be greater than mod A, and mod A is, which is less than 1. So, this will give rise to a pole at z equal to e to the power alpha 0 t, but e to the power alpha 0 t which we call A, its magnitude is less than 1. So, it will give rise to a pole within unit circle. Okay. Similarly, all the poles will be unit circle, and since it is causal, ROC will be, if there is unit circle in the Z plane, there is one pole here, one pole here, one pole here, one. You take the pole nearest to the origin, nearest to the unit circle, and then go outside. It is causal, we already have seen. So, this will be the ROC because it has to be outside a circle, and it cannot include any pole. So, go to the pole which is nearest to the unit circle. All poles are within unit circle because mod of A, there is mod of every pole is less than 1. So, you take this and go out. So, unit circle is contained and it is outside a circle. So, it is both causal and stable, okay, and rational, because this will be of the form a 1 by 1 minus e to the power alpha 0 t z inverse. Next one will be 1 minus e to the power alpha 1 t z inverse dot dot dot. If you add all of them, there will be a polynomial in the denominator in terms of powers of z inverse. Numerator also will be, if you add all of them, simple algebra says numerator also will be a polynomial in terms of powers of z inverse. So, you get a rational form. Okay. Here mod z will be greater than e to the power alpha 0 t, that is, sorry, mod z will be greater than sigma 0 t, which is less than 1. Also from this it will be e to the power sigma 1 t, this also less than 1. All these are within unit circle, that is what I said. So, you go to the near one, which is farthest from the origin, that is mod is largest of all the poles, and draw a circle through that, and then ROC will be outside that circle, and that will not contain any pole, that contains a unit circle. It will be stable, because all the poles are within unit circle. So, if you start from this pole which is farthest from the origin, draw a circle through that and then go outside, it will contain the, it will meet the unit circle, because all the poles are within unit circle. So, your ROC will contain the unit circle, which means it is stable and it is going out. It is already causal, we have seen. So, it will be causal and stable, and obviously it will be rational, because if you have these kind of factors, if you add them, denominator by simple algebra will be a polynomial in terms of powers of z inverse. Numerator also will be a power of a polynomial after you add everything, it will be a polynomial in terms of powers of z inverse. So, you will get a rational form. That is the way to design by impulse invariance method. There are another method called bilinear transformation, some general method which we will discuss in the next class. Thank you very much.